We're live. How's sound? Sound looks good. Okay, back to the notes. Okay, so we just got started on lesson 3.2. We'll give people, by all means, if you're watching this on video, you can just pause the video and catch up. A square root of a number is the factor of that number that, when squared, results in the given number. So that's what square root means as a noun. A square root is a number. But of course, square root can also be a verb, right? I can do square rooting, right? You can use it as an action word. So I'm going to say 2 square root is factoring a number into its principal square root and it's like saying the square root of x is equal to, or it's the same thing. It's not really, I'm making it look like I'm saying an equation. How about I put an arrow? The square root of x is the same thing as saying what number times itself equals x. I should put a question mark on that. It's a question. So that's the answer I'd have probably given my alien friend who looked at that square root symbol in my work and didn't know what it meant. I say, what's that symbol? And I say, well, that's the symbol that when you put it over a number, you're asking the question, what number times itself makes this number? And if the number that you're talking about is a whole number, then you had yourself a perfect square to begin with, right? And that means that that number had a principal square root. There is one, you don't even have to write this one down, just for your edification. You know, another way, another question that this asks is, it's asking the question, if a square has area of x, how long are its edges? So there's a geometry way to define square root, right? If you want to find the square root of 25, you just ask yourself, okay, well, if I had a square that was 25 meters squared, how long are the edges? 5. There you go. That's a square root. Okay. And just like in lesson 1, or in lesson 1, we're going to be using prime factorization again. So here's how prime factorization is going to help us out. We would like to figure out the square root of 1296. My, that's a big number. It's a little past my times table, so I can't just think about my times table and go, oh, which of the perfect squares you usually find in the time table, right? They're where the columns and row of the same number meet, right? So 64 is where 8 meets 8. 144 is the bottom corner where 12 meets 12. Unfortunately, I don't have a times table memorized big enough for 1296. I don't know if you were online yesterday and heard the conversation we had where we talked about, I've seen classrooms in Europe when I visited there where the times table on the wall doesn't stop at 144, 12 times 12. They make kids memorize up to 20 times 20, which is wild. I wouldn't know. Quick, what's 17 times 15? I don't have that. But you ask me anything else, I'm pretty good. My 12s, sometimes I forget my 12s. I got to think about my 12s a little sometimes. But the rest I got. 11s are easy. 10s are super easy. 7s and 8s, I will make the occasional mistake with 7s and 8s. Every once in a while I mix up 7 times 9 and 6 times 9. And then I realize, well, wait a minute. One of them's got to be odd. Can't be that one. So anyway, determine the square root of 1296. Past my times table, what am I going to do? I'm going to make a factor tree. So 1296. All right, what do I know goes into it right away? You could say, well, it's even. There's a 2. Go bigger. 1 plus 2 is 3. 3 plus 9 is 12. 12 plus 6 is 18. It's got a 3 in it because 3 goes into 18. So that means if it has a 2 and a 3, it's got a 6. And here's something I kind of noticed. Like I said, I know my 12 times table pretty good. And I know 96 is 8 times 12. So if it starts with a 12 and then it ends with a number that's a 12, it has to have a 12. So that's where I'm going to go. It's got a 12 in it. Okay, 108. That's the better number. It's not 18. It's 108. If you're writing in pen, just sneak a little 0 in between the 1 and the 8 for me, would you? Now, how do we break down 108? Oh, well, that's got another 12 in it, right? Isn't 108 in the 12 times table? Isn't it 9 times 12? I think it is. So 9 and 12. There we go. Now we've got the factors. Oh, it's not 3 cubed and 2 cubed. It's 3 to the 4 and 2 to the 4. That's why it looked too small to me. Okay, there we go. Come on, pen. And then this is 2 times 6, and that's 2 times 3. Yeah, there isn't, this is the right answer. It's 2 to the 4 times 3 to the 4, not 3's. My apologies, guys. I miscounted. So back up. Now, oh, this one's actually much easier now, and I'm still going to get the answer that I had in my head the first place. It's 36, because this is like saying it's 2 squared. I'm going to do a different power law than I did a minute ago, because now I have the right number. It's 2 squared squared times 3 squared squared. And then I'm going to use the fact that, again, I can make that power of a product. I can say it's the product of these two things squared. And there it is. What number squared makes 1296? Whatever 2 squared times 3 squared is. Or, come on, pen. Or whatever 4 times 9 is. That's why it's 36. Oops. That's not what I meant to write. 36 squared. Therefore, let me write this better this time. There we go. That's better. I knew it was 36. But then I thought to myself, wait a minute. I have extra factors. And then I realized this number I had wrong the first time. There we go. Okay, so that was example 1. That was actually pretty hard for example 1. This one's actually easier. Because this one, okay, first of all, I got to make a factor tree for 1764. What do you think? It's even. It's got a 2. 64 has a 4 in it, so I think it's got a 4 in it. So I'm going to say it's got a 4 in it. 4. How many 4s go into 17? 4 of them with 1 left over. How many 4s go into 16? 4 of them with none left over. How many 4s go into 4? 1. There we go. Now, is 441 prime? No, it's got a 3 in it, right? 4 plus 4 plus 1, 9. It's got a 3. So let's take the 3 out of it. Oh, I guess while we're over here, let's finish that branch. There. Okay, now let's take the 3 out of 441. How many 3's in 4? 1. Carry the 1. How many 3's in 14? 4. Carry a 2. How many 3's in 21? 7. Is that prime? 7, 11, 12? No, I think we got another 3, don't we? How many 3's in 14? 4. Carry the 2. How many 3's in 27? Is 49 primed? No. It's 7 times 7. Okay, so this is 2 squared times 3 squared times 7 squared. So once again, if all of these bases have the same exponent, I can call it one big multiply to that exponent. I can group them by power of a product law and say that that's 2, come on, Ken, 2 times 3 times 7 squared. We totally should have started with this one. This is a much easier example than the first one. And then quick, what's 2 times 3 times 7? 6 times 7? 42. Good. See, you're faster than me with that one. 7, sometimes I forget my 7s. 42 squared. Therefore, the square root of 1764 is 42. All right, so that's square rooting. Question? No? Oh, sorry. It looked like you had a question. Okay. Any questions from home? All right. Let's move on. Cube root. Cube root. The cube root. Cube root looks like that for a symbol. And I would say in words, a cube root of a number is the factor of that number that would multiply by itself twice. Come on in to equal the original number. So in other words, the cube root of 27 is 3 because 3 times 3 times 3 is equal to 27. And maybe I'll just write it up here. Just like square rooting is the opposite of squaring, cube rooting is the opposite of cube. And hopefully you know that the word cube is just like the shorthand nickname for taking something to an exponent of 3. And again, you don't have to write this part down, but if I had a cube, come on cube, if I had a cube and I knew that it had a volume of 27 cubic units, then I know all of the edges must be 3, right? Because to get the volume, you go length times width times height. Length times width times height. So you can undo that by going the opposite and saying, all right, if I know the volume's 27, how long are its edges? 3. All right, so now, once again, we're going to use our factor tree. What's the cube root of 216? Well, 216, if I make a factor tree for it, well, let's see, what goes into 216? It's got a 3 in it, right? 21 and 6, 2 plus 1 plus 6 is 9. So it has a 3 in it, and it goes in there 72 times. Oh, and I know 72. That's 8 times 9 for my timetable. So that's 2 times 4, which is 2 times 2, and 9 is 3 times 3. So take a look. I have 2 cubed times 3 cubed. And once again, that means I can group that together as 2 times 3 cubed, which is 6 cubed. Therefore, the cube root of 216 is 6. All right. Here's a slightly different question. Determine if 7. Am I going too fast? Let me move back down. Let me know if I'm going too fast. Okay. Yep. Scroll up a bit. Back to the words. There we go. Here, I'll put them both on the screen at the same time. While I'm showing you the screen here, notice that again, you don't have to write this part down. Just draw it in different colors so that you know that you don't have to write this. This thing here, this radical bracket, it's called a radical. I don't know if you used that word in grade 9, but of course, the radical, when you don't bother writing a number on it, has another invisible number here. It's got a 2. Right? I just assume that when I see that bracket without a number, it's a square root. But if I want a cube root, of course, I put that on it. If I want a 4th root, which is asking the question, what number times itself again, times itself again, and times itself again, so that there's 4 of them, makes a number, well then I'd say it's the 4th root. And of course you can do a 5th root and a 6th root. Of course, numbers have to get really, really big before they'd have a sixth root, right? 2, the smallest number that matters when it comes to this sort of thing, 2 to the power of 6 is 64. So 64 has a sixth root of 2. But try to think of what the next perfect power of 6 is. Quick, what's 3 to the power of 6? 3 to the power of, so 3, 9, 27, 81, 243, that gets me to 5. 729, am I right about that? 729? So there you go. So the sixth root of 729 would be 3. What would the next one be? This is why we tend to stick to square roots and cube roots. After that, they start getting to be really big numbers. All right, example 4. Is 1728 a perfect cube number? I don't know. Let's make a factor tree and find out. 1728 has a 2 in it. It has a 4 in it. Let's start with the 4. Right? 4 goes into 17 4 times, carry the 1. 12 times, so 3, and then 8 twice. So it's 4 432s. That's still got a 4 in it. Let's take out another 4. It goes in there 108. Notice that time I didn't forget the 0. And that, we already did this number. We know that that 108 is, what was it? Is 9 times 12? So let's break this up. So the 4's become 2's, the 4's become 2's, the 9 becomes 3's, and the 12 becomes 4, 3, 2, and 2. So let's put it all together. 1, 2, 3, 4, 5, 6. 2 to the power of 6. And then 1, 2, 3 times 3 to the power of 3. So I ask you, have I got a perfect cube here, yes or no? And then logically, can you tell me why you think so? What are you thinking? There you go. You're probably thinking, well, yeah, I got a cube. There might be people going, well, yeah, I got a cube here, but that's not a cube. Actually, it is a cube, right? Because it's 2 cubed squared. Or even better, let's write it the other way. It's 2 squared cubed. There, that's better. It's 2 squared cubed, right? So if it's 2 squared cubed times 3 cubed, put that all into one big bracket, and it's 2 squared times 3 all cubed. So it is 4 times 3 cubed, which is 12 cubed, which is equal to, sorry, let's write that the same way we did the other ones. Therefore, the cube root of 1728 is 12. Therefore, yes, 1728 is equal to 12 cubed. So it is a perfect cube. What would have happened in this question if it wasn't a perfect cube? Well, then I wouldn't have gotten exponents that are multiples of 3 when I did this. So let's see what happens on number 5. Is 540 a perfect square, a perfect cube, or neither? Well, let's make our factor tree. 540 is definitely, it's got a 10 in it. Let's take that out first. Come on. There we go. 54 tens. And 54, I believe, is 6 times 9, right? And that's 2 and 3 and 3 and 3. And, of course, 10 is 2 and 5. So, putting that all together, 540 is 2 squared times 3 cubed times 5. What is your conclusion here? Is this a perfect square or a perfect cube or neither? What do you think? Any thoughts? Do we have a perfect square? Do we have a perfect cube? Or none of the above? 540 is neither a perfect square nor a perfect cube. How come? Well, if it was a perfect square, all of these exponents, and why don't I actually I'll write the invisible one here. There. If it was a perfect square, all of these exponents would be even. Think about why that has to be. If it was a perfect cube, then all of these exponents would have to be multiples of 3. And they're not. 2's not a multiple of 3. 1's definitely not a multiple of 3. So that's it. It's neither. Okay? So there we go. Time for you to try some. So I'm going to stop my video. I might go back and edit out the part where I made a mistake. So let's see. Oh, no. Go back to here. Okay, so thanks for watching, everybody.